Time for Chapter 21, Podcast 8. So this podcast is basically going to mostly cover the Nernst equation in a voltaic cell. So we're going to introduce what the Nernst equation is, and so this is an equation where we can calculate the voltage at non-standard conditions. We're going to look at that. We're going to see how we arrived at that equation, and then we're going to apply it by working a couple of sample problems as well. Well, when we want to figure out what the Nernst equation is, just like many things in this chapter, we have to kind of go back and look at some of the equations that we picked up on from chapter 20. One of those being that our Gibbs free energy, right, at non-standard conditions is equal to the change in Gibbs free energy at standard conditions plus RT ln of Q. And so we also then can say, all right, if that were the case in chapter 20, right, if our Gibbs free energy and our standard Gibbs free energy are related in this way, well, what we do is that we're going to say that, okay, then if those are related to each other in that context, then our voltage and our standard voltage are going to be related in much the same way as that. Because remember that our standard voltage is equal to RT over NF times the natural log of K. So when we rearrange that to look a lot like our Gibbs free energy change one at the top, we get that equation there. And that's our Nernst equation. And we also find then that our voltage is equal to the standard voltage minus our 0.0257 volts over N times the natural log of Q, right? And again, this is at 25 degrees Celsius, 298 Kelvin only, right? If not, then we've got to plug in our R, our T, and our Faraday constant in order to calculate these problems. Well, we can now use the reaction quotient Q in our Nernst equation to look at whether our voltage is going to increase or decrease, right, depending on the value of our Q. Because we know that our Nernst equation is E is equal to E naught, right, minus RT over NF times the natural log of Q. Like we've done before, when we look at equations like this, sometimes we just need to plug in values, right? And so the top one, if Q is greater than 1, the natural log of something greater than 1 will be positive. All right, so what that's going to tell us then is that we have E naught, all right, minus, all right, RT over NF has to be a positive value, right? R is a positive constant. T is in Kelvin, it has to be positive. N is positive. Faraday's constant is a positive constant. All right, times something positive means that E is going to have to be smaller than E naught. All right, if we take the natural log of something less than 1, that's going to be negative. So our E is equal to our E naught minus, all right, our RT over NF is something that's a positive value times something negative. All right, well, E naught minus a positive times a negative is E naught minus a negative. Well, that's like adding, right? So thus the E, our new voltage, has to be greater than our standard voltage. And then if Q is equal to 1, well, the natural log of 1 is 0, which will make all of this stuff be 0, so E is equal to E naught in that case, right? Or our voltage is equal to our standard voltage in that case. Time for us to work a sample problem. This is sample problem 21-6, and here we're going to be using the Nernst equation eventually, right? That's what it says in part B. Initially, though, it just wants us to calculate our standard voltage. So to calculate the standard voltage, this is what we have done on previous problems in the past, right? What we're going to do is, right, look up values in our standard reduction potential table. Right, we're going to switch the sign of one of them, right, the oxidation one. We're going to add the oxidation and reduction steps together, and we're going to get an overall voltage, right, our standard voltage. In this case, our standard voltage happens to be 0.265 volts. All right, part B of the problem, though, now we're going to move into our newer stuff where it wants us to write the Nernst equation for our cell. If I want to write a Nernst equation, right, what that is doing E is equal to our standard voltage minus RT over NF times the natural log of Q. So it wants us to just kind of plug in everything that we know at this point. Well, I know that my E is what we're going to solve for probably eventually. My standard voltage is 0.265 volts minus, all right, RT over F. We happen to be at 25 degrees Celsius, so I'm going to say RT over F is 0.0257 volts, right? We're at 25, so I can use that. Divided by N. Now we finally have to calculate that N. N is the number of moles of electrons transferred. That is the number of moles of electrons in one of our half equations. So in the top one, I see 3 electrons. In the bottom one, I saw 4. But I'm able to get these two equations to balance each other out. The electrons have to cancel each other out. So the top equation, notice, is multiplied through by 4, and the bottom one by 3. So that the 4 in the top equation times the 3 is equal to 12. And the 3 out in front of the bottom equation times 4 is also 12 electrons. Now remember, for our N, it is the number of electrons in one of the half reactions. You just got to make sure that they are balanced, though. And so for one of them, it's 12. This answer is not 24. It is 12 moles of electrons. All right, to finish writing out the Nernst equation, I'm going to write out the natural log of Q, which is going to be products divided by reactants. And so I have the concentration of our nitrate raised to the 4th power times the concentration of strong acid raised to the 4th power divided by the partial pressure of NO to the 4th power. Water's a liquid, we're leaving it out, just like we have all semester long, times the partial pressure of oxygen cubed. And that is our Nernst equation. So probably the hardest part of that is just figuring out the N, the number of moles of electrons transferred. So make sure that we can do that. Continuing our sample problem 21-6, it wants us to now in part C calculate our voltage under, all right, not standard conditions. So it gives us the conditions that we're going to calculate this under.
gives us the concentration of nitrate, gives us the pressures of nitrogen monoxide and oxygen, and then it gives us the pH. So like usual, right, we've got to figure out what the concentration of H plus is from that pH, and then we can plug in everything into our Nernst equation. So if we want to find our H plus concentration, right, that is 10 to the minus pH from our acid-base chapters. So 10 to the minus 2.85 is 1.4 times 10 to the minus third. All right, so now we're going to say E is equal to, or E naught, 0.265 volts minus 0.0257 volts over our N, which was 12, times the natural log of our Q. All right, so we've got to plug everything in. So the concentration of our NO3, or nitrate, is 0.750. We're going to take that and raise it to the fourth power. Don't forget to do that in your calculators. Don't make those small mistakes. Times our H plus concentration, which we found to be 1.4 times 10 to the minus third. And that is also raised to the fourth power. All right, divided by, all right, the partial pressure of our nitrogen monoxide, which is 0.993. That is cubed times the partial pressure of our oxygen, 0.515 to the fourth power. We're plugging everything into our calculator. Double check your math on this. Make sure that you get the same thing that I do. And we end up with 0.319 volts as our final answer there. So using the Nernst equation, we can see that our voltage is actually going to increase when our conditions are laid out here in part C, when we're no longer at standard conditions. We've actually increased our voltage. Sample problem 21-7 is very similar to the last problem that we worked, except that instead of us solving for a new voltage, right, what this is stating in here is at what pH is the voltage 0 if all other species are at standard concentration. So we've got a little bit of a wrinkle in this problem because we're not looking for our new voltage. We're not looking for a standard voltage. What we're actually looking for is a pH when our voltage is 0. So it tells us that we're going to start by writing the two half reactions, and we're going to need our overall voltage, right? Our overall standard voltage. So just like we've done all chapter long, we're going to calculate the oxidation and redox. So oxidation and the reduction steps, and we're going to add those two things together, and I get a standard voltage of 0.071 volts. Then I'm going to write this out as a Nernst equation. I'm going to say, okay, the Nernst equation here would be E is equal to E naught, and our E naught we just solved for, so I might as well just plug it in, saying 0.071 volts minus, all right, good news, up here at the top we see that we are at 25 degrees Celsius, so I'm going to say that this is 0.0257 volts divided by our N. All right, so N, this is 2 times 1 electron, so that's 2 electrons. Double check on the bottom. I have 1, there's no coefficient out in front of the whole thing, times 2 electrons is 2 electrons. So that's going to be 2. And then now we've got the natural log of, all right, products. So H2S concentration divided by, all right, so our bromide ion concentration squared times our H plus concentration squared as well. So that's our Nernst equation. Now we want to figure out what the pH is. So again, if we want to find the pH, we're going to have to find the H plus concentration, right? That's what we're looking for eventually to get the pH. If the voltage is 0, when all other species are at standard conditions. So let's see what we need to do for that. continuing sample problem 21-7, we want to know what is the pH, so we're solving for our H plus, when our voltage is 0. All right, not our standard voltage, because we're not at necessarily standard conditions, right? Because some things are at standard conditions, but we want to know what the H plus concentration is. So we're going to take our Nernst equation, and we're going to set our E to be 0 in the Nernst equation. So 0 is equal to our E naught that we found, which was 0.071 volts, minus 0.0257 volts over 2. That's the number of moles of electrons transferred. Is the natural log of Q. All right, so our H2S concentration was standard conditions, so we're going to say that's 1 molar. And then on the bottom, right, we had our bromide ion concentration at standard conditions, which is 1. So 1 squared times our H plus concentration squared. The H plus concentration is what we're looking for. Now I'm going to rearrange. I'm going to say, okay, negative 0.071 volts is equal to negative 0.0257 volts over 2 times the natural log of, all right, 1 divided by 1 squared is 1 over our H plus squared. So we can make both sides positive. And we're going to end up with then 5.525 is equal to the natural log of 1 over H plus squared we're going to take e to the both sides, and I'm going to end up with 250.9596 is equal to 1 over H plus squared, or 0.00398 is equal to H plus squared. So H plus is 0.063 molar, and we can take the natural log of that to finally get that the pH is 1.20. So the pH would have to be 1.20 in order for us to have a voltage of 0 for this problem. All right, so that's going to conclude podcast number 8. It also concludes everything on voltaic cells. Our final podcast, podcast number 9, is about 6 slides long, and it is about, right, our electrolytic cells, right? The other type of cells. We waited until all this time in order to get into those, and we're going to see how they differ from our voltaic cells next.